Bueno, luego ya no va a colocar.
Okay, so welcome back to another session, last one. You're probably tired now, but so I will try to do my best to make a nice presentation. So I think I'm going to start with this, which is something that I mentioned in the morning. So this, but in the morning I showed just a picture, a static one. And this is the graph. And this is the interactive dashboard that I was mentioning in the morning. So this graph here represents the reaction network of the system. And the nodes are the different minima, intermediates, and also products could be. So if now, unfortunately, now you don't have access to this, but in a moment you will have. Let me just explain this in my computer. And look, if you now hover over the nodes, you see you can get information on. I don't know if everybody can see this. Probably in the back, nothing probably. But I should probably start by. Maybe I should start by. Okay. Let me start by. Yeah, doing something else. I have a repository in GitHub, and I have an HTML like this. So you can clone the repository in your computer. So you can do something like git clone. I mean, you should best probably first create a directory. I'm going to do it. Okay. Can you see anything from there now? Not much. Now? Everybody can read this from the back. No. Yes or no? No? The problem is the size of my screen is not enough. Okay, let me try. So if you type git clone and then the name of the repository, which I forgot, let me check. I mean, for the name of the repository, you can Google my name, Martínez-Núñez, and then GitHub. Okay, you type Martínez-Núñez GitHub, and this is my repository, GitHub. You click there. I have several repositories, and you go to the one with the name of the school, M2D school. Okay, click there, M2D school, and then you just clone it. You click here to copy the name of it. Okay, so are you familiar with GitHub? No. Yes. No. For those of you.
I sent yesterday the link.
Okay. So in the link, click here, code, and then click here to copy the name of the repository. Okay. And then once you have done that, just git clone, and now the name, and that's it. No, already exists. Sorry, let me. Okay, in my computer already exists. Let me do it in my directory, git clone. So you clone it here, and you have everything there. So everybody has done this. Everybody knows how to do it. Git clone and then the name of the repository. And then for the name, if you don't want to type all these things, go to the link that Juanjo sent you yesterday. You will have everything there. Now you will have a directory with the name of the school, M2D, and then you have another one named automaking, and then let me go back. Okay, and then in AMK tools, so you go to entity school, automaking, AMK tools, and here you will see an HTML, which is the one I was showing you before. This one you can use. I don't know if they have in CCC, Firefox or something, or any other web browser. But if not, you can download it to your computer and try to open it with your web browser. I mean, this is the HTML I was showing you before. So this is available to everybody. Okay, it is there. Entity school, automating, AMK tool. Okay? I don't know if you have Firefox here. No. But you can download it to the computer, and then you can open it. The best browser is Google Chrome. Best browser is Google Chrome. This one. And once you open it, you will see something like this. Any problems to see this or not? Is there any problems? No. Everybody has access to this? Yes. In the back, people in the back. Can you hear me? Can you watch this? Can you see this in your computer? Yeah. Good. Perfect. So, as I said, now that you have it in front of you, you can see all the possibilities. Obviously you can translate it. You can make it bigger or smaller using the the menu here. And then if you click on a node, for instance, you click on min2, the one by the name min2, the one in the middle. On the right, you see the structure. Okay, you see the structure on the right.
Can you repeat where the Firefox file is located?
Okay, it is here. It is here. So empty school, automating, AMK2. So you see, you can visualize the geometry. Then you can click here on the left where it says load vibrations. You load the vibrations, and you can and here you can select a particular vibrational mode, and you can visualize the motion of the mode. Some of them have symmetry, so you can rotate the molecule and so forth. So this is the minimum of the system, the global minimum. But also you can click on an edge. An edge is a transition state, right? So you click on an edge like this one here, TS29, for instance. Sometimes you have to click twice. Here it is. Now this is TS29. This is clearly a transition state. Look at the hydrogen. This is hydrogen transfer. Okay. Now you click on load vibrations, and the first one that appears is the one corresponding to the transition state. So this is the imaginary frequency. Okay. So this is for the hydrogen shift. Okay. Motion. Now, but you can also have a look at the other ones. They are listed here. But typically, this is the most interesting one. Right? So you click wherever you want. You click on a node, and this is minimum. You click on an edge, and this is a transition state. And you have the geometry, you have the frequencies, you have all information here. This is very useful because of that. All information that comes out of automaking can be visualized like this in an easy way. Right? I guess it is an easy way, or a better way than looking at the numbers and things like that. Now, another possibility is to have a look at the energy profile. You can click down here, energy I don't know what it says, but something, it says something down here, but I cannot read it.
Show
Profile. You click on show profile and you can see the profile, okay? The energy profile. Now, obviously, as I said in the morning, that in some cases like this one here, it is very dense in some parts of the energy. Like here, for instance, there are many structures with the same energy, etc. So because here you have everything connecting the minimum, global minimum with any other product. No, sorry. This is for indole, and this is just all connections between the minimum and the NH2 radicals. Let me click on a product like this one here. Yeah, NH2. This is NH2 as well. This is just like a subset, like a smaller part of the reaction profile where where you have only the connections between the minimum and the species like this. So NH2 radical plus the rest of the molecule. Okay, and these are all possibilities connecting the minimum with these molecules, because you might be interested in studying reactions leading to NH2 radical. You can also generate a similar graph for connections leading to any other product. Then you can generate different kinds of graphs like this. Now, as I said, again, the energy profile. Maybe suppose you are now interested in reactions that happen with an energy lower than 150 kcals per mole, for instance. So you can filter the reactions here, the pathways here. You can type 150, and then, oh no, what I did? No, sorry, I made a mistake. You can recover it, like clicking there, recover the original one. And now 150 energy filter. You click on energy filter, and all the pathways with energies above 150 disappear from the graph. Okay, disappear from the graph. What else? You can also filter by species involved. For instance, suppose you want minimum 12 for some reason. You want to, filter pathways and by a given molecular species, like minimum 12. So you have to click here on the left, minimum 12. By the way, if you click here, minimum 12, and then locate molecule, you go to the part of the graph where the molecule is in the graph. Here, and it puts the molecule in the center of the graph, like minimum 12. Suppose you are interested in minimum 12. And then you say, okay, filter the pathways by this minimum. And then you click on molecule filter, and some paths disappear as well. Because now what we have is only paths containing some point, minimum 12. So this is another possibility. There are more possibilities because this is all graphical, but this has been generated using a command line script. And with a script, you can tell, for instance, and this is by default, by the way, is just the paths with a maximum number of 4 steps. Right? You can see, you don't see any path with more than 4 steps. This is 1 step, 2, 3 steps, 4 steps. Right? And by the way, the last one, as you can see here, the last ones are barrierless. There is no barrier between this minimum and the products, and the same here. The last one is barrierless. In this case, it could be barrierless, could be with a barrier, but in this case, they are barrierless. So there is 1, 2, 3, and 4 at most. There could be some of them could be with only 2 steps, 1 step. Here you see only with 4 steps. But this is the maximum. You can change that. If you want to get, I don't know, all pathways with maximum of 6 steps, for instance, you will get obviously more nodes, more pathways, because you will have more paths connecting this what I call the source and the target. The source is the initial node, the starting molecule, and the target is the product. Okay? I don't know if you are more or less following me. Yes. So this is graphical. Everything is graphical, as you can see here. But again, with the command line in the script, you have more options. All the options are. There is another GitHub repository. It is here. Let me show you. And which one is it? ANK tools. Yes. Again, if you Google GitHub AMK tools, you will find it easily. It is here, and if you click on user guide, you can see all possibilities. You can also employ some of the libraries to make something even more complex. And these are different possibilities. You can include barrierless reactions using this option. You can include vibrations or not, because obviously the file will be heavier, or if you include the vibrations or not. So you can include them or not, depending on your system. And then this is very useful: paths, source, and target. You can here. This is the way this is the way in which I generated the previous HTML. So with the option minus paths, you specify the source and the target. The target could be a chemical formula or a label, because chemical formula is more general. Like I want to get like NH2 plus, I don't remember. I'm going to make up a formula because I don't know. C5. This is omega. This is NH2, and the other one, because I don't know how many atoms of each type we have. Something like this. And then you will get all the isomers corresponding to this. Okay. But if you put a specific label, like PR 150, for instance, or PR 102, this will correspond to different isomers. This will be one isomer, this will be another isomer. So in the target, you can use just a chemical formula, and in that case, you get all of the different isomers, or a label. How do you know the label? Okay, you go to the graph, you click on the node with the corresponding label, and you see what you have there. If you're interested in a particular isomer, you have to put that particular label in the target. I don't know if you see the difference between both cases. This is more general, or you get more things providing the chemical formula, and with this you get a particular, because this, I mean, there could be more like 2 or 3 labels corresponding to exactly the same chemical formula. The difference is just the isomers, because we have different isomers here with the same chemical formula.
One thing I have question, that if you click on the 102 minimum and 1050, you click here.
Yeah, you have to uncheck that. But you check and uncheck that the show profile, okay, to visualize the geometry or to visualize.
No, it wasn't that. It was that if you click here, there's no path to here. As it should be this path. No?
Why do you say there is no path?
Because if I click now here,
but you have to go back to the original. Yeah, I need to do it again.
Yeah. For example, if I click, I'm seeing and I'm understanding this way. That
So you have to type here the name of the species you want it to appear in the profile. Just type there.
You have to reset, no, everything.
Yeah, well, this is what you have to reset, but then you have to type there now you can locate the molecule if you want, and now you can click on find the molecule. And then you will see only the paths containing that.
if I click another one,
Yeah, but then you have to reset again, go back. Do exactly the same thing.
and so that you can like distribute.
You can discriminate, filter,
Okay.
read of paths you are not interested in.
Okay, it says.
Yeah, so this is I am starting from let's say the last part, because this is while you do the calculations, this is the analysis, right? But I guess this is useful. And as I said, look, for instance, the way I can generate this, I'm gonna show you from my computer. The program is installed in this computer. This is a laptop. AutoMaking is installed here. Here, have Windows and I have Ubuntu also. This Linux distribution, Ubuntu in Windows with WSL2. You can install Ubuntu and I think other distributions as well. But with Ubuntu 20.04, I guess, at least Ubuntu 20.04, it works. You download. I will show you the wiki in a moment. You download the script and you can install it in your own computer. And if you do that, look, this is the way in which I can generate. I know I have to first. I have to run the script. So basically, this script is very useful because I put everything in a singularity container. This is a container with everything: the libraries, the dependencies, AMK tools also. And this script, what it does is it tries to find an image, a singularity image in your home directory. In my case, I have one image, so it was very fast. If it doesn't find the image, it will download the image from the Singularity repository, the latest one, which in our case is 1135. This is the latest version of the program. So it will download it from the Singularity image, and then it will check for the presence of other programs, like Gaussian, QCore, for instance. In my case, I don't have the programs installed on my laptop. Obviously, this is not to run ab initio calculations, so I don't have Gaussian or QCore, but I have low-level calculations. So this is really fast and useful for many people. So if you, for instance, have, well, these ones are not yours, I guess. If somebody has your, I mean, if you, for the people who have their own computer, you can try this procedure if you want. So it's simple. And it tells you what you have in this environment. So you have, obviously, the latest version of the program, and also, okay, I have Gaussian. I forgot. I have Gaussian 09. What I don't have is Gaussian 16. But I do have the G09. This one I have. But it tells you you don't have the latest one, Gaussian 16, and also you don't have QCore. That's okay. But I have the Gaussian N. So and you enter in a kind of environment with all the possibilities and all scripts for the program. And for instance, if I go to one of the tests, now let me go to this one. The way to generate, this is just to show you how to use the command line script to generate the HTML. You use this script here, AMK view, and then you have to tell the program where the reaction profile, sorry, where the reaction network is located. In my case, it's here in this directory. I will tell you about that in a minute. But you have to tell the directory where all the data is collected. The reaction network that is going, I mean, we are going to parse this file with all information on the reaction network. And then you can tell -b, which is please include the various reactions or not, if you decide not to include them. And then, as I said before, -- paths. So give me all the paths connecting minimum, this one, I think minimum one, and all the different paths. Because this is a small system, if you don't put the target, it will give you all paths connecting this source with all possible targets. Because this is a small system, I can do that. I wouldn't do that for Indole because it's a very rigid system. But for this is formic acid, by the way. This is a very small system. I have only, I guess, like 10 or 15 transition states. So I can do that for this system, for this example. If you don't specify the target, it will give you all paths between the source and all the other nodes. I hope it works. If you didn't make a mistake, it is going to work. Yeah, it takes a while, but it should work. Yes, here it is. And now you will see a file by the name network HTML. And this is the file. You can change the title also. You can change the name of the file. And you can use -- title and a name, or just rename it, whatever you want. But this is the name of the HTML, network HTML. This is the ones I was showing you. Not exactly the one. This is a different one. But this is the procedure to generate the file. Again, you have to tell the location of the reaction network file, the reaction network file. I will tell you about that in a minute. Don't forget. Don't worry about that. Then I want to include the various reactions, and I want all paths connecting minimum one with the other nodes. So this is the way to, so it is very easy to generate. And also, again, I think there is the option to change the number of elementary steps is minus depth. So what is the depth of the pathway? What is the depth? So shall we go until 4 steps, 5 steps, 6 steps, whatever? So this is depth, minus depth option. By default is 4 steps maximum. Okay, 4 steps.
I think it is minus cutoff.
Cutoff, sorry. Yeah, cutoff.
Yeah, it is
Cutoff. Yeah, you are right. Absolutely right. Yes, because this I think that depth is in a different color. Yeah, sure. It is minus cutoff. Yeah, thank you for that. Minus cutoff. Yeah, it is in the repository. It is there, all the information. Now, what can we do now? Well, you have several. Well, let me go back to the computer in which you have an account, because what I was showing you was this laptop. You can run everything in a laptop. But now let me go back here. So AMK2. These are the different possibilities. Now let me go back, and then we can go, for instance, to FA worked example. Oh no! First, let me show you something, because some of you, the problem here is because we don't want to collapse the computer because we are too many people. So, I mean, submitting jobs is a critical point, because we are 40 people here. I don't know how many online. And so you can use the CCC account, or you can use another account. This is a computer that we have in Santiago de Compostela. This is just for testing purposes. So we are not supposed, I mean, was not meant to, I mean, this was not for 100 people submitting jobs at the same time. This is just to show the possibilities of the program. So I am a bit afraid that we might collapse the system. Anyway, the thing is, the web page is I don't know if nobody's going to see this. It's RxN King for reaction kinetics, USC.S. I can tell you again. I mean, for the people in the back, I go there in a minute and I will tell you it. AMK. You can go there and then click on login register, and you can register with your email account, and you will receive an email, and you can activate an account. But please don't do anything until I tell you, because as I said, this is not to submit like 100 jobs at the same time. So, RSN, everyone is here. So you can go there and register. And then the idea would be that, I don't know, maybe half of the class can use this, and then the other half can use the CCC. I don't know. But anyway, once you have the account, I mean, to register, you click on register here, and you enter your email, the institution, project. You don't need to type anything there if you don't like, and that's it. And wait until you get an email to activate the account. I have my account, and I have already 2 examples that I have already run: acetamide and glyconitride. The way to submit a job here, and this, I mean, for instance, this half of the class, everybody can use for instance, this server now, and the other people can use the CCC. Again, people online, I don't know.
Probably CCC is better.
Yeah, the CCC probably. The way to submit a job is click on new job. This is a new. You click on new job, and then you can put there a molecule. This is by default. This is formic acid, but you can search molecules by the name here. Or you can just upload a molecule. There is a possibility. If you right-click here, you can upload different files there. Or you can just, I don't know, for instance, methanol. And here is methanol, etc. So you can just pick one molecule. Molecule will be there. This is the geometry of the molecule. And then you have to choose some parameters. Well, the charge, if it is neutral, obviously is 0. And then this is for the kinetics. For the kinetics, there is these two choices. The number of possibilities here is obviously not the same as with the command line scripts. You have more possibilities with the command line scripts. But just to see what you can get, you can use this. So temperature or energy, you can use temperature or energy. And this is for the kinetics only. So for instance, if you want to see many things, it is better to use an energy. Because temperature, for instance, if you put temperature 300 Kelvin, obviously at 300 Kelvin, you are not going to go over barriers that are, I don't know, higher than 20 kcal per mole, for instance. So it is better to put an energy and then, I don't know, maybe 300 is okay. And then you will see many, many things. Just to see things. This is not like something you... And then you can change here the number of tasks. Number of tasks and number of iterations. This is something that I was talking about in the morning. This is number of iterations. Number of iterations, we can use just 2 iterations because we want something quick, 2 iterations. And then number of tasks, this could be like, look, number of tasks means number of, this is not number of trajectories. Every task will have 5 trajectories. So you have to multiply the number of tasks by the number of trajectories. Each task will be submitted to one processor. So if you put 10 tasks, you will need 10 processors. If you put 100 tasks, I think you are not allowed to put 100. Let me check the maximum. Maximum is 20. 20 is the maximum. But please don't put 20. Maybe 5 could be enough or something like that. Or 10. 10, maybe 10. I'm not going to do it just to allow you to do it. And that's it. And you can write something here, like the description of the job. And then you submit the job. Yeah. And once you do that, well, I'm going to do it just to show you test. Just to show you what you get. You will get something like this. First, you will see you know, the status is still waiting. So it's probably because you already, let me see. Let me refresh here. I'm still waiting. Okay, in the meantime, I can, for the other half of the class, I can tell you how to submit the jobs in the CCC system. If you go to FA, look, for the other half of the class, with the account in CCC, you can go to FA STD-MD, or standard MD. FA STD-MD. You go there, and there is a script, which is launch LL, which I prepared in the morning. Launch LL. Here you load the module, and then you submit you submit the same thing. You submit 10 tasks and 2 iterations, like in the web server. 10 tasks and 2 iterations, exactly the same thing. And that's it. So you just need to execute this script. You have to make it. You have to change the permissions, chmod +x, and then the name launch LL. And once you have done it, you can launch it. Okay, SQ. Mine is waiting. No, now it's running. Look, this is running. So you can do it like that. This is for the other half, because we want to get results. Everybody, I mean, this way everybody in the class will get a result. Hopefully. Let me see the. Oh, this is still waiting. I guess this was not a good idea. But maybe you were quicker than me. So maybe your calculation now running and mine is waiting. I don't know. What about the other people? Are your calculations running or? Yeah, good. Because I don't mind if mine is stuck there. It doesn't matter. I have to wait. And what about the other half?
You can replace you can replace page maybe.
If I don't?
If you replace page, maybe
Refresh, you mean?
yes,
No. This is prepared to, I mean, this web page is prepared to refresh every 10 seconds. But still, I mean, you can do it. That is prepared, people do it. So, how do you say it? This is what they told me. This I haven't done. And still wait. Anyway, today. Sorry. The terminal. Yes. All I have done here is, I mean, you have to be here. Look, automating SA standard MB, STD MB. This directory. And once you are there, you change the permission of the script, chmod plus x, and then launch ll.sh, and then you just execute it. So you have to do /launch ll. That's it. Now you can type SQ. And yours is still yeah, because this is for many people. I can cancel my. I can delete my calculation because I have the results already, and I'm gonna do it. Let me do it. I can cancel it. Good. I don't know, maybe you are now there. Okay. In the meantime, while we wait, okay, please. Quiet, please. Be quiet, please. While we wait, let me explain you the input files. I guess they are important, and the output files. This is, I guess, interesting, right? So this is the input file. So this is the typical input file. It is also in the tutorial. You can also read the tutorial. You should read the tutorial if you want to use the program and you want to use all the capabilities. You should read the tutorial actually. But this is obviously this is the time to tell you about this. Okay, so this is the input file, one of the input files. The other one is just the geometry of the system. But this is the main file, main input file. So there are several sections, as you can see: general, method, screening, and kinetics. General section, there is always the format here is like a pair of keyword and a value. Okay, the keyword is the first one, like molecule, and then there is a value, which could be a string, could be a number, integer, or it could be a real number, whatever. Float. So in the first case, so the first one is molecule, and then the name. I try to use acronyms for the systems, like FA for formic acid and so forth. So something short and indicative for the type of system you're studying. So molecular and FA. The name FA is very important because then you are supposed to have an XYZ file with the same name, FA XYZ. So if you put there FA in lowercase, you have to use here lowercase as well, because this is case sensitive. So you have to use exactly the same name .xyz for the geometry. Okay, exactly the same as the value for the molecule. Okay, so this is molecule. The name of the molecule. Then there is many keywords are very easy to understand what they mean. No, this is low level. Again, this is case sensitive. The keywords. So else are in uppercase, and then the other ones lowercase. Low level means the low level you want to use. There are only two choices here. The first, by the way, the first value is the program, and the second one the method. Program can be MOPAC or QCore. MOPAC or QCore are the two possible choices for the low-level calculation. The two possible programs for the low-level calculations. MOPAC or QCore. MOPAC, there are many MOPAC, there are many possibilities. You can check the different methods. Typically, you have methods like PM1, PM3, PM6, PM7. For PM6, there is a family of methods with dispersion included, with many things. You can go to the web page and see the different options that you have there. If you don't put anything, this is the default, PM7, because this is the last one, and this in principle, this is supposed to be the best one, the one which is parameterized with the largest number of data points, of data. So PM7 is the one we are using. But you can use QCore. In QCore, you don't have these methods. The only method that you have is the only semi-empirical method that you have is XTB. So this could be the other option. But MOPAC is included in the distribution. So if you want to use MOPAC for the low-level calculations, you don't need to install anything else. If you want to use QCore, you have to install QCore. The way to do that is also in the wiki page, which I'm going to show you in a minute. There are too many things, and I want to go step by step. There is a wiki page with all the instructions, how to install QCore, etc. But if you decide to use QCore, you have to install it beforehand. Otherwise, it's not going to work. Now, high level. For high level, obviously, you need something like Gaussian or, again, QCore. You cannot use automating without any other high-level, program that provides high-level initial calculations, or DFT calculation. In this case, this is because this is an example. I selected the program Gaussian 09, and this is the method. A very simple method with a very small basis set, just for example. Okay. So low level, high level. Just be aware that depending on the program, you need to install it or not. If it is MOPAC, MOPAC is there. For the other ones, QCore and Gaussian, you need to install the programs. Then this keyword here, there are many keywords, but these are just the most important ones. In the tutorial, there is the full list of keywords. Okay? These are just the most important ones. This one here, high-level reaction network. This is an important one because, as you can imagine, doing things at low level, this is not very costly. This is quick. It takes minutes or hours in the worst case. Hours could be. But for the high-level calculations, if you want to recompute everything at high level, this could take weeks or months, depending on the system. So you can either use AMK tools to filter paths and etc., and just compute at high level only the paths of your interest, or you can use this keyword. If you put here complete, it means do the complete thing, do everything. This is an example again for acid, very small system, you can do everything, high level. But you can use here, you can also cut out transition states with high energy. You put here reduce and then a number, and then reduce, suppose you put reduce and 55. It means that you are going to reduce the network, and you are going to throw away transition states with energies higher than 55 kilograms per mole, above the minimum, the lowest minimum. Okay, so this is a way to reduce the system, the network. Then IRC points, it means the number of IRC points that you want to compute. So this is the number of points from the transition state to the minima, to both minima, one side and the other. This depends on the program. For Gaussian, well, this depends on the experience of the user and also depends on the reaction. For some reactions, only 20 points or 30 points are enough. For some other reactions, which are very complex with many rearrangements, you might need something like 40, 50 points. In any case, after the last point of the IRC, there is an optimization of the minimum. So even though you put there just something like 29, it doesn't matter. In many cases, it doesn't matter unless you have bifurcations or things like that. You will end up in the same minimum. But this is the number of IRC points. This obviously depends on the system. I put here 29. And why 29 and not 30? Because and this is something that could be changed in the future, but not now. It hasn't been changed so far. The thing is that for the computation of the IRC, you compute the Hessian every 10 points. And this is the reason for using 29 there. Because at point 30, there is another calculation of the Hessian. So I don't want the Hessian. I don't want one calculation for the Hessian for just one extra point. That's why 29. Because it could be also 39. Again, in the future, it could be nice to have also a keyword just to tell how many, what is the frequency for the Hessian evaluation. But this hasn't been done so far. Right? This is why I put here 29. Now, charge and multiplicity of the system, like in many programs. And then this is the method. Method is like MD for molecular dynamics. This is standard MD. Could be BXDE for the other method that I mentioned in the morning. Then temperature with this interval, you don't need to put this. You don't need to put anything here. Actually, this is something a bit strange. Well, not a bit strange. This is something which is not very elegant, I would say. I mean, in the input file, you put nothing here, but then after a while, the program will change the input file. This is not typical, and I guess, and I admit that this is not very elegant, but it is the way it is. I decided to change the input file because this temperature range or energy range is changed depending on the reactivity. This I mentioned in the morning, and I know this is to some people this is surprising because they don't put anything here, and then after a while they check the input file and they see a line with this. This is done by the program. Sorry for that. This is the way it is. So this interval is going to change at runtime. But you don't need to specify anything, as I said. Depending on the size of the system, this will be determined automatically. And then the number of trajectories per task. Each task will have 10 trajectories. You can change that, but I guess it is not a good idea to change that number. Because some people say, okay, why not 100 trajectories? It is better 10 trajectories. The reason is because each of these trajectories, each node, I mean, these 10 trajectories, they all will have the same energy and they all will start from the same minimum. Okay, so we prefer to have more tasks and less trajectories to sample things better, rather than having here like 100 trajectories, all with the same energy, all starting from the same minimum. Okay? I don't know if you understand what I'm saying. So it is better to put 10 trajectories, and the more tasks, the better. Right? So that's why if you have more processors, this is better, because each processor will take care of one task with 10 trajectories, maybe, with the same conditions. Not the same conditions Q's and P's. No, they differ. So you have the random number seed is different for each of the 10 trajectories, but they all have the same energy and start from the same minimum. Right? So they will sample a given area of the PES, of the potential energy surface, and then another task will start from a different minimum, maybe from the same one with a different energy. But this is why it is better to have here just 10 trajectories is enough, and then use as much tasks as possible, depending on the computer, on your computer. So 10 trajectories is good. It's a good one. And then you need some parameters for the screening. Sometimes you don't want transition states with imaginary frequencies lower than 200. This is what it means, this line here. This means throw away transition states with imaginary numbers, imaginary frequencies lower than 200 wave numbers. Some other cases you want those transition states, but this depends on the case. For instance, if you study organometallic catalysis, homogeneous catalysis, where you have metals, obviously frequencies there are very, very low. You can have something like 50 wave numbers, 40 wave numbers. You don't want to put here 200 wave numbers. That depends on your system. Okay, I put 200 because this is an example again, and I don't want here to have frequencies of van der Waals complexes doing things that I'm not really interested in. I don't want to study complexes here. I have another option to study complexes, van der Waals complexes. But this is again to filter structures that I don't want. So this is a threshold for the imaginary frequency. So imaginary frequencies are going to be greater than that, 200 wave numbers. And these three things here, they are employed to compare structures and also to compare, as I said in the morning, when the molecule is intact or when you have fragments. So the first two ones is to compare different geometries. This is a threshold again. So you compare different things. You compare the energy, you compare the frequencies, and you compare, if you remember from my lecture in the morning, the eigenvalues of those matrices, of the adjacency, and also the sprint coordinates. And you have a set of numbers. You compare those numbers, so you can get. I don't remember what this stands for. I guess this is like an error. This is the maximum. I don't remember what type of error, but this is the maximum one, and this is the this is the maximum one, and this is the average one. Error of what? Error comparing this set of numbers that I mentioned. Energies, frequencies, eigenvalues. So the lower these numbers, it means that the structures need to be really, really similar for the program to consider them that they are the same structure. So, but these numbers here, typically they are good numbers, just to start with. If you see strange things, like the program is throwing away structures you want, you have to change those numbers and increase the value. This is, and also the last one, this is the eigenvalue of the Laplacian. Remember that? Because in the morning I didn't explain everything in full detail. I said that the number of zeros, like if you have two zeros and then different numbers, you have two fragments. But this is okay when you use integers for the matrix. But you can use numbers. You can use elements which are not integers. For instance, for the adjacency, you can use a number between 0 and 1, depending on the 3D geometry of the system. And in that case, you don't get exactly 0. You can get 10 to the minus 5, 10 to the minus 3, 10 to the minus 2. And this is the threshold, like 0.1. If a number is lower than 0.1, that's a 0. This is what this means. Right? And again, you have to look at the structures. You have to look at the structures that are discarded because they are fragments. For transition states, for instance, I use that to discard fragmented structures, which are transition states with frequencies which are low in some cases. So either with this keyword or the other one, the idea is to discard those structures. Okay, and then finally, this is the parameter employed to run the kinetics. In this case, I put energy, like in the example that this part of the class is doing, and then 150. I think you put 300, but it doesn't matter. This is the energy of the system, and it puts all molecules, it gives all molecules the same energy, and it tries to see what the fragments are, and what is the branching ratio for the different fragments. I will show you the results in a minute. I suppose that for some people the calculation's already finished or not. Yeah, good. So we can now have a look at the results. So the idea for those of you, the idea is that you should have something like this. You should have something like this. Here you see the statistics for the calculations. So how many, this is the CPU time for each task and things like that. There is a workflow with different tasks like the MD simulation, the IRC calculations. And here you see the breakdown of all the CPU time for every single calculation. Okay? This is just the calculations. This is the optimization of frequency calculation of minimum. This is the reference structure, and this is the number of iterations. The important things are actually not in this directory. You should have a directory with the name. With the name final. There should be a directory with this name, final LLFA. For those of you using the web, you can download data, and this is the final directory. You download data, and data is a zip file with the final directory. Final, the name final means obviously that this is the final step, and in the final step, what I did was to collect all the interesting data there in final. Okay, so you go to final. For those of you who already finished, you go to final, or for the people using the web, you download the data. This is the final zip directory. So you go to final. The name of this is final LL, and then underscore, and then the name of the molecule. Okay, in this case is FA. If you decide to use another name, the name of the directory will be different. So this is the interesting thing. What's inside is the following. So you have one file, convergence.txt, and here you just have the statistics. This is the number of iterations, number of transition states, and number of trajectories. It is 100 trajectories in this case because we employ 10 tasks times 10 trajectories per task. This is 100. And then in the second iteration, this is the total number, by the way. This is a cumulative number. This is 200 in total, and this is 10 transition states. So in my case, you will see probably different results, by the way, because this is stochastic calculation. Everybody is using a different random number. And now if I run the calculation again, I probably get different numbers here. Obviously, the idea is to use more tasks and more iterations, and in the end, you will get the important structures will be there in our case. But this means that I got only 2 transition states in the second iteration, because we have 10 here and 8 there. This is just the statistics. No? This, if you want to plot how many transition states to get versus the number of trajectories, this is what you get. No? This is the file to plot that. And what else? Then there is something which is obsolete here, like for instance, energy profile. You don't need it because you have these AMK tools. Forget about energy profile. It is much better to use the interactive HTML. The same with graph all, graph king. This is, I will probably in the future change that because this is not useful. Now, kinetics is something interesting. This file. Here you see the final branching ratios. Now, for our molecule, this is simple because this is formic acid, and you see only 2 channels here. One leading to CO plus water, the only one leading to H2 plus CO2, and this is the branching ratio. Okay? Using our conditions. Remember, this was 150. Maybe you get something different. People using, well, depending on your molecule, you will get different things. For formic acid, 150, you should get something like that. Okay? But again, this depends. This is stochastic. Depends on the number of tasks, the number of iterations, but should be around that. So around 99% is going to be CO plus water. And this is just the time. So this is the population of each species as a function of time. This is time in picoseconds. This is the population. I started with 1,000. You can change that also in the input file. There is a keyword for that. I mean, changing that basically, I mean, this is to plot. I will show you the plot in a minute because the plot is also there. But this is to plot like population for all the species. This is the reactant. You can have some intermediate with some population, and then the products. And just this number here are interesting. I mean, are interesting. You can change this number. You can make it bigger if you want, because the larger the number, the smoother is going to be this curve. Okay. If you put there something like only 10 molecules, you will get many fluctuations like that. This is just, obviously the statistics will be better and you will get something like that. So this is the population of the species, this is the starting minimum, there is an exponential decay here, minimum 3 is an intermediate, that probably the population goes up and then back again after some point. Yes, it goes to 70 something and then it goes to 0. And these are the products, CO plus water and the other one. So this is a simple case. And this is what you get. Now, population. Look, if you want to see the plot, this plot, you can use. You can watch it. This is population 150. The name of this file is population. Then comes the temperature or the energy of the system. In this case, 150, and it is a PDF file. And let me see. Yes. So this is exactly this one. So this is the minimum in pink. Then there is this intermediate in blue, and then this is one of the products in green, the predominant one, and then there is this other one in orange, which is CO2. And the other one, the green one, is water. So this is the population plot using the data of the other file. Okay. This is just, I mean, obviously you can make a better plot, but this comes with automaking also. Now, more interesting things. Yeah, the files that I mentioned before, like this one here, RxNet. This is reaction network information. This file, or another one that I will show you in a moment, these are the ones that are employed by AMK tools to construct the graph. So this is the graph information. Every single row here shows shows an elementary step. Okay, one elementary step. For instance, the first one, this is the label for the TS. This is the energy. The zero of energy is the starting geometry. This is the zero of energy. Okay, your starting geometry. The one you put at the beginning in the XYZ file. This is the zero. Okay. Now, this is the energy corresponding to that zero of energy, related to that zero of energy. And this is the reaction path information. So transition state 1 connects CO plus water with CO plus water. So this is probably a van der Waals transition. I don't know, I have to have a look at it. But probably it's a van der Waals transition state with no interest. Now, the second one connects minimum 1 with minimum 2 and so forth. So these are the different connections. This is the detailed information of the reaction network, which is employed by AMK tools to construct the graph and everything. So this is the information of all the connections. Now, there is another one, which is CG. CG, this one here, is smaller. You can see that you have only four paths here. So RxNet, this is important. RxNet, there you have all in RxNet for reaction network. You have all the structures. I mean, all the conformational isomers are there. For instance, for formic acid, which is this system here, you have a cis and a trans cis. You have the cis. I'm not going to draw the double bonds and things like that. No? But for the chemists, I tell this just for the chemists. This is the cis and this is the trans, right? And these are conformers. In the other file, both of them are there. One was minimum 1 and the other one is minimum 2. In this other one, there is only minimum 1. Look, because minimum 1 is which one? Is this one, the trans. The trans is the most stable one. So minimum 1 is only there. Why? Because what we do here, CG is for coarse grain. What we do here is to group together all the conformational isomers. All the conformers go in a single node. Because this is, and typically what I do when I analyze the results, is I use this file for the HTML. Why? Because typically the transformations between conformers are very fast compared to jumping a big transition state for breaking or forming bonds. This is typical case, but this depends on the system. Right? Be aware of that. But so this is what I'm doing here. So I am just merging all the conformers in a single node, in a single minimum. So instead of, in terms of energy profile, the real profile could be something like this, suppose, and then something like that. This is the RX net energy profile, right? You have 1, 2, 3, 4 conformers, and then you have here another minimum without any other conformer. In the CG situation, what we do is we say, okay, this doesn't exist. I have only one minimum. This is what I'm doing there. Right? Which one? The lowest energy one. From the family of conformers, I take the lowest energy one, which is minimum one in this case, and this is the one that stays there, right? Minimum one. And that's why you don't have so many pathways, because the other ones, there are pathways in the other one, connecting this with the other, this with this other one. But in the kinetics, this is going to slow down the kinetics a lot in the kinetic simulation. This is something that I didn't tell you, because in the KMC simulation, if you conserve all the minima, if you do a simulation with this, oftentimes what happens is that you spend all the time jumping from one to the other, and you never jump this one. So you spend a lot of CPU time doing this thing, and you might not be interested in that. So it is a good idea sometimes to group together this minimum. This is why I use CG, okay? And CG is for constraint. So that's why you see fewer paths there. And then also you have, well, where is the minimum? The minima information is here. So you have min info file, min info. In min info, there is a list with the minima, in this case 5. And then the energy. Look, minimum 2 is the 0 of energy. Minimum 2 is the cis. Is this one, the cis. Yeah, I decided to use the cis one, not the minimum energy, not the lowest energy trans isomer, just to show that the 0 goes in the starting geometry. It's not the global minimum. It doesn't need to be the global minimum. It's the one that you select, that you put there at the beginning, starting one. And this is the 0. The other one is 8 kilocalories per mole more stable, according to the semi-empirical calculation. This should be run at high level. And this is the information of the conformational isomers. Look, in each line, you see the different families of conformers. So the first one is minimum 1 and 2. They are both conformers. And then 3, 4, and 5, they are also conformers. Okay? They can be interconverted by rotations of single bonds. Now you have exactly the same file for the transition states, which is this one here, like 10 transition states in my case. You might find a different number there depending on the case. And also, there are also conformations for the transition states. Sorry, different conformers also for the transition states, okay? And this is the list, and this is the energy, and these are the conformers. But again, this kind of information is only here, but most of the information is in the interactive HTML. Most of it is there. This, for instance, this thing of the conformers can only be found here, but the other things are there. What else?
Emilio, can I say one important thing? 1 minute?
Yes, sure.
So, one thing, Ines sent an email like 10 minutes ago with a link to a document where you need to fill your name, surname, email, and passport or gift. So please do it today, because this night I will send this information to the IT office, and hopefully tomorrow everything will work more or less, let's say better, no? Better than today.
But don't do it now. Wait 20 minutes.
But let's say after the lecture.
And then there is there is 3 important files, which are 3 databases with all the information of the different structures. And these are these ones here: tsdb.db, There should be another one. Yeah, this one. Min.db. These are databases with all the information, and this can be accessed very easily using using a script. We have to load the module first. Automaking 2021. Huh? Automaking. I didn't spell it correctly. Okay, here it is. Now you can use, for instance, select.sh. You have to go one directory back. You have to go to the working directory or app. So you have to be in the working directory, not in the final directory. And once you are there, you have to tell which is the final directory and which is the minimum you want to, which is the table, for instance, minimum DB, and all. Let me check because I forgot. No. Check. Jump. MTS1. Sorry. Yeah, here it is. So the way to get information is this one. You use this script here. Select SH, then the name of the directory again. Why you have to put the name? Because if you run the high-level calculations, which we are not going to do today, but if you run the high-level calculations, you will see a similar directory with the name final HL and then the name. This is once you finish the DFT or initial calculations. Same structure, everything is the same. But you might want to get the geometry of the low-level structures or the high-level, doesn't matter. So you have to put the name of the directory, then you have to say, okay, I want the geometry of TS1, and this is the geometry of TS1. Or you can get everything. If you want everything, just say, I want all of TS1, and you get all. And all means there is an ID. The ID is just the label of the TS, 1, 2, whatever. Then number of atoms, this is constant in the system. And then the name, energy, this is the energy of the semi-critical calculation. So it's not very informative. Then the 0-point energy, then the Gibbs energy. So we submitted a calculation at 300 Kelvin, but still this calculation, this Gibbs energy, is at 300 kilograms per mole. And this is the value of 300 Kelvin. If you used in the kinetics something like temperature 1000 Kelvin, then this would be the Gibbs energy for 1000 Kelvin. But if you decide to use in the kinetics a microcanonical simulation, this is the Gibbs energy at 300 Kelvin. It would be a different Gibbs energy if you select initially the kinetics for a different temperature. Okay, and now this is the geometry, and these are the gravitational frequencies. You can do the same for the products also, for the minima also. For instance, all prod 1, and for prod 1 you have exactly the same thing plus the formula. This is a product means here fragments, fragments, and this is the formula. You can do that from your computer if you want. Select SH is the name of the script. But this is just to get the numbers, okay? Of course, the geometries, you can visualize the geometries using the HTML, but also you can go to a directory inside final. There is a directory normal modes. You go to normal modes, and you can use molding to visualize also the geometries and the normal modes. So there is two ways to visualize the geometries, using the HTML or using molding. I guess molding is available in CCC, right? Module load molding, maybe. Yeah, like this. Okay, and now molding. Okay, good. Now molding, for instance, minimum 0001. What I did, I padded this the name with different zeros because I wanted to see the everything sorted out. Right. I mean, from 1 to, otherwise you see 10 here, then 1, 2. So that's why I decided to do this padding with zero there. So now you can, you need an Xterm running in the computer, but if you use mobile Xterm, this should be fine. So you can see also the normal modes and everything here, okay? Of the transition states, of the minima, and all these things. And this is an out-of-plane mode, so you have to rotate the molecule. Transition states, for instance, the first one was like a transition state connecting two van der Waals structures. Let me check if that's the case. Yes, this looks like a van der Waals structure, right? So this is nothing really very interesting from a kinetics point of view. Well, I don't know. It's 485 point numbers. I don't know. But the interesting thing, as I mentioned in the morning, is that you get both unimolecular and bimolecular reactions of transition states, because this is dynamics, and the dynamics means that you can know, for instance, with the other method, you are going to see or to get only unimolecular reactions. But with molecular dynamics, what you do is you put the molecule in the sky up here, with a very high energy. And this will sample, sample regions of the potential energy surface, which means different regions, which means that the molecule can start here and maybe after some time can land in a completely different minimum energy path, which connects maybe A plus B leading to C plus A, and you end up in this other one. Okay. I think this is more or less the kind of results that you should expect from, I don't know if I forgot something. Okay, the barrier reactions are here. Let me show you. There are two reactions in this case, and they give to the same product, OH plus C. CHO, this is just alphabetic order, by the way. This is not chemistry, nothing like that. So automating uses for the chemical formulas. It uses the alphabetic order, right? The chemical formula. Yeah. And you have two possibilities from minimum 1 and minimum 3, which is the breakage of the CO bond. Okay, this is the breakage of the CO bond. You can tell me why the CH bond is not broken, because by default CH bonds or OHs, they are not broken. You have to tell the program to break the bonds, and it is easy to do that. But by default, I don't do it because there are many breakages like that. But it is possible to do it. In the tutorial, there is a way. There is just a keyword you have to use to tell the program to break also the OHs or the CHs or any other type of heavy atom H bond. Okay, but by default, only this type of bonds are broken. And again, this is not included in the kinetics. The barrier reactions are not included in the kinetics. And the reason is because, as I said in the morning, it is possible to do it, but you have to do it by hand. Not easy to calculate the rate coefficient for the dissociation leading to OH plus HCO. This is not easy to do it in an automated manner. You can do it by hand. The reason is because you have to locate variationally the transition state. You have to pay attention to how you treat, for instance, this bending. This is a transitional mode. This is called transitional mode. Transitional because it transitions from a vibration to nothing, or to a rotation, sorry, not to nothing, to a rotation in the products. So this is bending, and when you break the bond, this bending becomes a rotation of the OH, right? So somewhere in between, this is not a vibration, this is not a rotation either. So what is it? So this is like a Hinder rotation. How to do that automatically? No simple answer. So that's why this is not included in kinetics. You can do it. We can do it. I did it in the past. You have to check. So how should I treat these things like the transitional modes because they are the most important ones. They are low frequency modes, and they are the ones that impact the most in the value of the Gibbs energy. The Gibbs energy I mean, the value of the Gibbs energy depends a lot on the low frequency vibrations. Okay, anything else? I had more examples here, by the way, but this is like a typical calculation. This is like a standard calculation with a standard MD and all things. There are many other possibilities. I can tell you the wiki. Sorry, I forgot the wiki. It's important. But by the way, the web also provides the graph for the particular case, the graph that I mentioned before, and also provides a report. In the report, there is just like a summary of the results. But the interesting thing is in data. Data is the final directory, and then obviously you can delete your jobs, etc. Now the wiki page. The wiki page is this one. I mean, from the server, you can go, if you log out from the server, here you go to wiki, and that's the wiki page, okay? This is the easiest way. Okay, there is like an introduction, the team, license. Here is how to install the code. This is the interesting thing for most of you, I suppose. For those of you who are interested in trying AutoMeching, this is the first step. Install the program. These are the instructions to install NQSQ core. These are the instructions. This is very easy. You have to use Conda. This has not developed in my group, by the way. This is developed by any other group, but this is very useful for us because they have XTB, and it is a very convenient semi-empirical calculation. It is better, probably better than the methods implemented in Mopac, so it is very useful. Okay, this is the auto installer. The auto installer is this automeching.sh that I mentioned before. This is the one installed in my laptop. You can install it in your laptop. If you have Apple, you can. This is different distribution. But if you have Windows or if you have Linux, you can do it. Okay? And then you can use this thing, this script. In the script, there is everything. You can take it. You can take the script from here, using this command here. Then you make it. You change the permissions of the script, and you execute it. And once you execute it, the first time it will download the latest image of from Singularity repository, and then it will create this kind of environment that I showed before, and that's it. In the container, everything is there. AMK tools is there. You don't need to install AMK tools. So this is useful probably for starting to get familiar with the program. If you want to install it in a workstation, I should probably try to install from the source. This is probably better to install from the source. And the instructions are here. And this is just a script to install in CentOS, for instance. So everything is also there. How to install the program, the dependencies, everything is there. There are many dependencies. I admit there are many dependencies. And there are several tests as well. This one is the one in FA, but you can run several other tests. Like other possibilities. This one, ASOC, is for association. You can study van der Waals complexes and get the different complexes of different energies for a couple of molecules, for a timer, for instance. This is ASOC. And then there is also the possibility to use external forces to bias, to trigger a particular chemical reaction, because this is to study reactivity in general. But if you want to study a particular chemical reaction, you can use an external force to trigger a given reaction. And then this one here, program OPT. This one is this. You have to be careful if you want to use it, because depending on the size of the system, it could be very demanding. This is to do the sampling and the simulation using semi-empirical calculation. But once you have the guess structure, you run the optimization using Gaussian high-level calculation. So this is like a mixed procedure. where you sample you do the dynamics using low level, but once you get the TS structure, the TS guest structure, you use high level to optimize the structure. So this is more demanding, obviously, but you start to do high level calculations at low level. I guess this question is similar, relates to one of your previous questions. So this I forgot. So this is possible, but this depends on the size of your system. Then there is van der Waals. Van der Waals is different from a SOC. A SOC means that you get the minima, all the minima between a pair of monomers. You have a timer and you want to get the minima. With van der Waals, this is more powerful because you get not only the minima but also the transition states. So you sample van der Waals. For instance, you have the example that comes with the distribution is a nitrogen molecule and benzene molecule, and you get all the structures for these two. For this time, nitrogen and benzene. And you get the transition states and the minimum as well. Then CK is for chemical knowledge. This is an example with the chemical knowledge module or method. Again, for formic acid only. The questions in the morning, people asking me proteins and things. Haven't tried proteins so far. Biggest system I tried so far, not me, but a student in the group, was the timer of C60. And this is 120. Atoms at most. Can we study proteins? Maybe. I don't know. That's the matter of trying. And then BXDE also. So there are different tests and different possibilities. And so this is the wiki. And I was going to tell you something else now. I forgot. I was going to tell you. This is the work example. Okay, yeah, this is something that I forgot to mention. You see, there is, well, I don't know if you have questions now or things you want me to discuss or to explain you some practical questions or details of the, no. Yeah, just let me tell you something about the torsions or the conformational sampling. Because the algorithms are to break and to form bonds, right? So you might ask yourselves why I'm speaking of these conformers since we don't have any algorithm to find these structures. Right? In the MD simulations. This is like you find the structures because you end up landing in different structures, and also because you have we do scans of the torsional angles also. This torsion here directory in parallel with the MD simulations, we run scans about the dihedral angles or about the rotatable bonds, the ones with single bonds, around the single bonds. And that's why we have this directory, and we also try to sample the conformers in this way. So this is like the conformers are like a side product of the results of these simulations, but also we do these scans to try to find the conformers of the system, and they are done here in torsion and directory. You look tired from your faces. Any questions? Anything? There are many things I can tell you, other things, but I don't know. Everybody got their results in the sense that from the web or from the CCC.
Yes.
And well, I don't know what time are we supposed to end this? At 8 or something like that? Well, I don't know. Questions now? Any questions?
Yes,
Yeah, you asked all your questions. Okay. Yeah, we did Again, if I wanted to do the same calculation now, I wouldn't use exactly the same. At that time, I used the NTC, but it was complicated because there were many components. Catalyst, it was a cobalt catalyst. It was the catalyst, CO, but it's important. So what I did was to take all the binary systems made up of the catalyst plus something else. And then you get simulations for every single small concept or something. And then I did that in all the combinations. Then what I did at the end was to learn all the smaller networks into the big one. And then I run the kinetics of the this is efficient. That's why if I have to do it again, I would go everything is the same problem. And then try to find all the possibilities, like you ask for the explicit part of the catalyst, maybe select the reactions and the other things. This is pretty much if you use a distillation, you will get the H2. This is very difficult.
I mean, we can.
With explicit solving in a more technical. I don't know. It is possible. It is possible. But actually, this would be like refining the structure. So this could be done in the second step. When you run the high-level calculations, you can do EFT or high-level calculations and do the solvent, but explicit solvent. Explicit means putting water or something else. This is also possible. In that case, it would be better to use DXT. Because if you use standard MD, what is going to happen is the evaporation. This is the use of it. This is evaporation. So the DXT is different because you keep the system, less, let's say, and the water is there. And also you have an option to you can put like a spring connecting the solid molecule to your molecule and avoid evaporation. Yeah, like a harmonic to avoid evaporation. So you can include that. But this is within years, which at the moment is lower. But it is everything is possible. No problem. No problem. Darío? Bueno.
Una vieja.
Pero bueno, acaban de instalar su puede ser, puede ser. De la Universidad.
Hay que poner lo que vamos a hacer. Y ahí es como lo
I sent an email in case you want to join this. Tonight we're going to have dinner in the center and maybe one here. I sent the link to your friend by email in case you want to come. Please, no, sí, mañana que tendremos que